So we'll work this example out in detail. So to do that, we'll kill this. Green seems to be writing well, so we'll continue with it. So we have our regular S3, and I'll write it up again. Where we'll leave sigma and tau off to the side, right? They're listed here. Tau just flips 1 and 2, and sigma's a rotation. So now we have two subgroups. The subgroup, let me just use the same labels as he does. H. And I want to prove that that's a normal subgroup. Well, how many cosets will the system have in total? How many elements in here, and how many elements in the group? How many cosets? Only 2, right? So obviously, EH and sigma H and sigma squared H are all just H, right? Because they're in there, and it's closed. So those are all the same coset. So I need to pick an element that's not in here to generate my cosets. What's an obvious one? Tau. H. Well, that's easy because the way the group is structured, what am I going to get as my coset? Tau times Z times epsilon is just tau, and then I get tau sigma, and then I get tau sigma squared. That's easy because those are built in. But now let's look at what happens if I do it the other way. H tau. Well, I get tau, but then what's the next entry? It's sigma tau, right? And the next entry would be sigma squared tau. But these are not written in the standard way, right? That and this are not elements of this thing, because we're not assuming commutativity at all. In general, permutations don't commute with each other. Functions don't commute by composition. So we have to actually figure out what sigma tau is. How do we do it? 1, 2, 3, there's sigma, there's tau. So when I compose these, what do I get? One goes where? Where do I start? Do the composition.
First to the right.
So 1 goes to 2, and then
2 goes to 3.
Now I have to worry about what 3 goes, right? This guy doesn't touch 3. 3 goes to 1. That's it, right? And where does 2 go? 2 goes to 1. Goes to 2. So that's actually sigma tau. And let's compute the other one. Sigma squared tau. Well, we have sigma squared up there. It's 1, 3, 2. And then tau 1, 2. So where does this send 1? To itself, right? So because 1 goes to 2, but then this guy sends 2 back to 1, so 1 goes nowhere. How about 2? 2 goes to 1, and then 2 goes to 3. Where does 3 go? This guy doesn't touch it. 3 goes to 2. So that's it. So that's, now, what are those elements actually in the group? Well, these are the real elements in the group. What is tau sigma? Well, that's 1, 2, 1, 2, 3. So where does this send 1? One goes to 2, goes to 1, 1 goes nowhere. Where does this send 2? To 3. And where does this send 3? To 1, to 2. So notice that this is exactly equal to sigma squared tau. And how about tau sigma squared? That's 1, 2 times sigma squared 1, 3, 2. So that sends 1 where? 1 to 3. This guy doesn't touch 3. Where does 3 get sent? 3 gets sent to 2, and then 2 gets sent to 1, so 3 gets sent to 1. And where does 2 get sent? To itself, right? 2 goes to 1, but then sent back to 2. And that's exactly sigma tau. So this guy is actually equal to, by our calculations, tau, comma, tau sigma squared, comma, tau sigma. So notice I got different results. Sigma tau is not equal to tau sigma, right, by our calculations. So the elements don't commute, but this is the same set as that. So this is the idea of normal. I don't have to get the same answer. I just have to end up with the same set. And it could be through a different bunch of operations. So this is a really, really good example of basic normal subset. Normal subset. So because this thing is normal, and obviously if I did any of these, right, times, I could build tau sigma with any of these elements in here. We're not going to go into detail with too much stuff, but it works, right? Okay, so we've shown where individually the elements don't commute, but I conclude that GH is equal to HG for all G in my group. We just showed it. The sets are the same set, even though they don't come out in the same order. And so the conclusion is, therefore, H is normal in S3, which means I can do arithmetic on these 2 cosets. It's not real exciting. So I've got this coset and that coset. I've got 2 elements, and this one acts as the identity. Not exciting arithmetic, but it works. That's the meaning of normality. Now let's prove that the other guy is not normal. Proving something is not normal, all I have to do is find the counterexample. So let's take K as the identity in tau. That's a subgroup because tau squared is the identity. What's an obvious thing to try? How about sigma K? What do I get when I apply that? Sigma and sigma tau. Right? What if I do K sigma? What do I get? Well, I get the identity is still going to be sigma, right? But I get tau sigma. Well, what was tau sigma? Sigma squared tau, right? And those aren't the same. I found one case where right coset and left coset are different for the same element. So we conclude by one counterexample that K is not normal in S3. Okay, so that's the idea of normal subgroups. Okay, let's just do one other nice example, general example of a normal subgroup. As a reminder of another interesting subgroup. If G is a group, Z of G is the set of all elements, let's call them H in G, such that G, H, H, G. This is the set of all elements in the group that commute with every element in the group. It's called the center of the group. And we proved a little while ago is a subgroup. You look back at notes. It's a subgroup because the identity certainly computes with everybody, so the identity's in there. And we showed by using inverses and cancellation that if H is in there, its inverse also commutes. So it's a subgroup. In fact, it's a normal subgroup. And the proof is easy. If I do G, Z of G, that's by definition the set of all G of H, such that H is in the center. Right? The right coset G, pick a particular element G and do that, well, that's by definition this, right? The set of all G times something in here. But it's the center of the group. So what is this equal to? By the definition that this is the center, what's GH equal to? It's equal to HG, right? Because every element in here commutes with every element in the group. In particular, it'll commute with this particular G that I chose. And what's this equal to by definition? Well, that's because the results commute every time, I of course get the same answer. So the center of the group we conclude is a normal subgroup. And very often the center is just the identity if a group's not very abelian. If a group is abelian, then the center is the group because everybody commutes with everybody in the abelian group. It's only interesting when they have a smaller center. And that's theorem too. If G is abelian, every subgroup is normal. Okay, let's see if we can give you a little bit of homework on this second. Maybe do one problem. this to wrap up. So your homework is to read, of course, and I want to give you specific reading because there's a lot here. You only have one more day of groups. So, study section 2.8, page 122 to 125 carefully. There's lots of examples and a few theorems, but you should have the background to do that. Up to lemma 2. And then homework. Section 2.8. Number 1A and 1B. Just to give you a little tour of that, I'm using the dihedral group, D12, which was listed back in the previous section. It's simply D12 has an element of order 12 and an element of order 2. And those are the only elements in the group as listed there. And it says, in each case, show that H is a subgroup and determine if it's a normal subgroup. So I just want you to do A and B. So that's your homework. And we'll finish with normal subgroups on Friday. Then on Monday we will have a quiz on a short quiz on Cosets, Lagrange's theorem, and normal subgroups. And push on to our last topic, which is quotient groups, which is what we really want to be. So, what are we heading for? This is what we really are after. This symbol, G mod H, is a set of all cosets, set of all distinct cosets of H and G. It actually is a group under the group operator if and only if H is a normal subgroup of G. This is why we care about normal subgroups. And there's the homework. I think we are good until Friday.